Hi, my name is Nur Shahira binti Ibrahim. I will give a brief introduction about HPLC. So, what is HPLC? High Performance Liquid Chromatography, or known as HPLC, is a technique that is used to analyze mixture by separating, identify, and quantify their individual components. Unlike traditional method, HPLC uses a high-pressure pump to push the liquid solvent through a column that packed with fine particles. So, this high-pressure system not only speed up the separation process, but it also gives a better resolution, making HPLC an essential tool in laboratory worldwide. So, this process works by exploiting the interaction between mobile phase, the liquid solvent, and also the stationary phase, the column, the material. So, each component in this mixture will interact differently with the stationary phase, causing them to exit the column at different times. So this is referred as retention time. So by analyzing this retention time, HPLC can effectively separate and identify the compound. This technique has found application in many fields, including pharmaceutical testing, food safety analysis, and also the environmental monitoring, thanks to its accuracy and versatility. The objective of our experiment is to determine the retention time of the standard solution caffeine and to identify the caffeine peak in the soft drink sample, and also to determine the amount of caffeine in the soft drink sample using the response factor method.
Let's look at the main components of HPLC. First, solvent reservoir. This is where we store the liquid, called the mobile phase, which carry the sample through the system. Second, pump. The pump moves the mobile phase through the system at high pressure, ensuring consistent flow. Next, injector. The injector introduces the sample into the system accurately. It can be manual or automatic. 4. HPLC column. The column is the heart of HPLC. It separates the sample components based on their properties. Number 5. Detector. After separation, the components are detected and measured. The detector converts this into signal. Next, PC or data system. The computer processes these signals and produces a chromatogram to help identify and measure the components. Finally, waste container. The liquid left the system and it collected in a waste container for disposal. Now, let's walk through the HPLC process. The process begins with the mobile phase flowing from the solvent reservoir through the pump and into the injector. Here, the sample is introduced into the flow, combining with the mobile phase. The mixture enters the column, where its components are separated based on their interactions with the stationary phase. As a component exits the column, the detector measures them and sends data to the PC. The PC generates a chromatogram that displays peaks for each separated component. The height and area of the peaks indicate the identity and amount of each component. After detection, the liquid is collected in the waste container.
Assalamualaikum and hi, my name is Imelda Damia binti Johannes. So right now, I'm going to present about the result of this experiment, which is experiment 6, HPLC. So, in the HPLC analysis, we observed 3 distinct peaks. The first peak was for the caffeine standard, followed by the peaks for the Coke and Levita samples. These peaks are crucial for identifying and comparing the caffeine content in each drink. So, how to read the peak graph? To interpret the HPLC graph, we focus on 3 main aspects. First is the retention time. This helps confirm if the detected compound is caffeine by comparing it to the standard. Number 2 is peak area, which is this reflects how much caffeine is present in the sample. And lastly is peak shape. A sharp and symmetrical peak suggests the compound is pure and correctly identified. So, this is the caffeine standard peak. Based on the peak, the caffeine standard had a retention time of 2.482 minutes and a sharp, symmetrical peak with an area of 6,249.49 milliabsorbent units. This peak served as a reference for identifying caffeine in the Coke and Levita presence of caffeine. The peak area of 17,001.12 milliabsorbents indicates the amount of caffeine in the samples. So now, this is Levita sample peak. The Levita sample had a retention time of 2.479 minutes, confirming the presence of caffeine. Its peak area was 1.11511 exponent 4 milliabsorbent, which is larger than the Coke sample, suggesting Levita contains more caffeine. Although Coke had a higher area percentage, Levita's absolute peak area was much larger. This means Levita contains more caffeine even though it has more ingredients that lower its area percentage. To calculate the concentration of caffeine ppm in the sample, we use these two formulas. First, to calculate the response factor RF caffeine standard, we need to divide between peak area caffeine standard with concentration of caffeine standard. Next, to calculate the concentration of caffeine ppm in the unknown sample, we need to divide peak area caffeine in the sample with RF. And the conversion factor is 1 mg per milliliter, which equal to 1000 ppm. Based on the provided formula, which are using the peak areas and the response factor, we calculated the caffeine concentration. For Coke, the concentration was 112.03 ppm, while for Levita, it was higher at 178.43 ppm.
For discussion, the standard caffeine solution was analyzed to serve as a reference for identifying caffeine in other samples. The peak shape was sharp and symmetrical, indicating the purity of the standard caffeine. These parameters set the benchmark for comparing the caffeine contained in other tested samples. The Coke sample had a retention time that nearly identical to the standard caffeine retention time, confirming the presence of caffeine in the Coke sample. The peak area was slightly higher than the standard caffeine, indicating a higher caffeine content. The sharp and symmetrical peak shape further validate the purity and presence of caffeine in the Coke sample. This indicates that the caffeine concentration in Coke is slightly elevated compared to the standard solution. The Levita sample retention time slightly lower than the standard retention time but close enough to confirm the presence of caffeine. The peak area was significantly higher than both the standard and the Coke sample, indicating a much higher caffeine content. The peak height further support the conclusion of Levita containing the highest caffeine concentration among three samples. The sharp and symmetrical peak shape confirm the purity of caffeine in this sample. Next, HPLC is highly sensitive and can separate multiple compounds in a mixture. In both chromatograms, several peaks with distinct retention times indicate the presence of multiple components, not just a caffeine. Peak at 3.601 minutes and 4.206 minutes are too far apart from caffeine typical retention time and likely correspond to other compounds such as phosphoric acid or sugar. Coke uses phosphoric acid for its tangy flavor, and it can appear as a peak at a unique retention time depending on the HPLC method, and high sugar content is common in the Coke, and sugar compounds may show up in the chromatogram. For Levita, peak at 2.799 minutes and 3.752 minutes suggest taurine, vitamins, or other functional ingredients as energy drink are typically fortified with this. Taurine is a common additive in energy drink for its role in boosting energy and focus. Energy drinks frequently include B-complex vitamin, for example B6 or B12, which could show small peaks. According to the findings, Levita had the greater caffeine concentration of 178.43 ppm than the Coke, which had a concentration of 112.03 ppm. This seems unusual because the area percentage of caffeine in a Coke, which is 57.36, is higher than in Levita, 17.70. Although these results seem unexpected, they are reasonable because Levita, as an energy drink, likely contains more caffeine than a Coke. We can prevent this problem repeated by verifying the preparation twice. We can ensure the samples are consistent and free from error before analysis. Next, repeating the experiments help confirm the reliability of the results. HPLC can be sensitive to small variations, so running the analysis multiple times ensure that the orientation time, peak area, and height are consistent and not influenced by random error or instrument fluctuations.
Now, we're moving to the conclusion. For conclusion, the finding demonstrated that HPLC is a reliable analytical method for quantifying caffeine in beverage, with consistent retention time and sharp symmetrical peak indicating purity and accuracy. Coke was found to contain 112.03 ppm of caffeine, while Levita had a higher concentration of 178.43 ppm. To improve reliability, factors such as sample preparation, metric effect, and area percentage should be carefully controlled. Take a look at 3 important applications of HPLC and how it works for each. So first one, separation of large molecule from small molecule. HPLC is widely used to separate big molecule like protein or polysaccharide from smaller ones such as sugar or amino acid. This is done using a technique called size exclusion chromatography (SEC). The column in SEC acts like a sieve, where smaller molecules enter tiny pore and take longer to pass through, while larger molecules move quickly and easy first. This makes it perfect for isolating large, natural products from small impurities, separation of homolog and oligomers. HPLC can also separate molecules that are very similar, like a series of related compounds, homologs, or small molecule chain oligomers. For example, reverse phase HPLC, RP HPLC use a column that separates these molecules based on their slight difference in polarity or size, allowing for precise analysis of complex samples. 1. Rapid determination of molecular weight distribution. When working with polymer or large natural product, HPLC can quickly measure the range of molecular size in a sample. Again, size exclusion chromatography is commonly used here. It provides detailed information about the distribution of small, medium, and large molecules in the mixture, which is essential for understanding the properties of polymer or analyzing natural product composition. These 3 applications highlight how HPLC can handle a variety of challenges in separating and analyzing complex mixtures efficiently and accurately.